Yes, thanks, Andreas. That was one of the titles I had before. I was initially asked to talk about hydrothermal rocks only by Andreas and Ilya, and the paper then kind of evolved a little, so I chose this more general title of Triple Oxygen Isotope Variation in Earth's Crust. And the idea was to provide you with kind of all the mechanisms that you need to be aware of when you study these materials. So we've heard something about mass-independent processes. Andreas Pack just nicely reviewed examples where AiO2 would make it into solids of the Earth's crust, but this is still exotic. So most of the processes we want to look at are actually mass-dependent fractionation processes. So these induce very small variations in the cap delta 17O, and we want to understand why that is and how we can use it. So initially, when you take any samples from the Earth and you measure 17O and the 18O, you will find that they will fall close to a terrestrial fractionation line with a slope of 0.52. This was the traditional idea of doing it. And then as more and more labs measured or tried to determine the exact slope of the terrestrial fractionation line, it turns out that the slopes from lab to lab differs, which is simply because each lab uses a different set of samples to define their terrestrial fractionation line, and each sample has their individual history. Also, these TFL slopes tend to have negative intercepts, and then they are usually shallower than the meteoric waterline, which has a positive intercept. So this, what we are seeing here, is kind of the variation purely due to mass-dependent processes. And if you plot it up like this with a small delta versus small delta, also moving to this delta prime notations here, you would not see this variation. So that's why we use the cap delta notation, which simply is the difference to, or the offset from a reference slope. And the reference slope I'm using here mostly is 0.528, but I sometimes have still plots in there with 0.5305, or even also the normal delta notations. What we're doing in this field is mainly looking at theta values. So we try to determine what the slope is for a specific fractionation process in this space. And if the theta value is different from the reference slope, you will induce some variation in the cap delta 17O. This is again the same thing. The theta is defined as the ratio of the logarithms of the alpha values for 17O and 18O. So it's basically this formula here that it's coming down to. You can calculate the fractionation factor for 17O by taking the fractionation factor for 18O to the power of theta. So we're interested in what the theta is for individual processes. One of the things that changes theta is temperature. It's slightly temperature dependent. So if you increase temperature, theta will also increase, and your fractionation factors alpha for 17 and 18 will decrease, and you end up with these curved relationships for equilibrium isotope fractionation. In my paper, I plotted some of the theta values for different processes, starting with equilibrium. So we have up here the upper equilibrium limit at 0.5305 by this formula up here, and we have a formula for the lower temperature approximation limit, which is not really strict. So we see that theta values increase also for empirical data with increasing temperature, but we also see that we have some theta values that are equilibrium theta values, but they are below this low temperature approximation. You can determine theta values experimentally by simply, for instance, taking minerals from a rock sample, analyze them for triple oxygen isotopes, and then see if they fall on a line. And if these minerals are in equilibrium, they should fall on a line with a corresponding to a theta value, which kind of makes sense from theory. So in this case, it's close to 0.529, and this is a metamorphosed BIF. and these minerals are apparently in isotopic equilibrium. And you can see on the plot on the right that if you do this with various rock samples, each rock sample has its own little mass fractionation line, and this induces the variation that we see in the terrestrial fractionation line. Depending on what material you use, you will get a different slope for all your samples. So you can actually check if samples are in equilibrium or not, and this idea was picked up by Kano et al. So Kano looked at mineral pairs in terrestrial samples here, plagioclase pyroxene and plagioclase olivine, and you can see that the theta values kind of make sense. They are close to what we expect for equilibrium. Maybe this one is a little bit low, but in general, the general picture is that these terrestrial samples have equilibrated mineral pairs. If you go to lunar samples, you see that this is not the case. So here we have theta values even below 0.5 and even above the high temperature limit. So this indicates these mineral pairs here are not in isotopic equilibrium. A word of caution for such analysis, we of course have very small fractionation factors alpha for such high temperature processes. So you have to be sure that your isotope analysis are really correct to make such a judgment. So it's in German we say it's a bit frickelig to do this, but I think it's a good way, one of the only ways to really check if your mineral pairs are in isotopic equilibrium, and then you can use it, for instance, to derive a temperature from it. So if it's not in equilibrium, you know that your temperature estimate is not useful. This is another example for equilibrium. Jordan Wostbrook analyzed these samples from water and silica samples from a geothermal power plant in Iceland. The geothermal waters here enter a heat exchanger, and in the heat exchanger we have deposition of silica, and Jordan Wostbrook measured the water which falls here below the meteoric water line, and then the silica samples fall on a nice equilibrium line at the expected temperatures here, obviously in equilibrium with this water. So this water is drawn down a little bit from the meteoric water line simply because the mantle or igneous rocks in Iceland fall in this position here. And so the equilibrated, fully equilibrated water would fall down here, and the geothermal waters that enter the power plant, they have exchanged with rocks. So they are driven down from this meteoric water line. So this is also the reason now I compare these equilibrium theta values with the slopes of the TFLs that have been put out, and also the MVL, and it seems that most samples used in these constraints are from equilibrated samples from the Earth's crust. So if you use a quartz sample precipitated at low temperatures, that defines the slope of the TFL, and it should turn around to be 0.525 or so. But there are also some lambda values that fall away from this equilibrium range. You can also produce such a slope simply from equilibrium processes by combining several processes. So this is an example where we have low T alteration and high T alteration of oceanic crust, holding the ocean water in a steady state. So we don't actually observe, or we can constrain these vectors here. The overall effect is then a vector that is outside the range of the theta values we expect for equilibrium, but it's simply because it's the overall effect from superimposed processes on each other, holding the ocean water in a steady state. So this would be 0.51 something. As isotope geochemists, we often look at kinetic fractionation versus equilibrium fractionation. And I think equilibrium fractionation is quite straightforward, but kinetic fractionation is not so much. First of all, we can look at diffusion, how diffusion is in this theta. So this line here, it's simply estimated from Graham's law, you can see that as the molecular mass of the diffusing species increases, your theta value decreases. Also, the theta value for H2O diffusion is a little bit lower than if you apply some more sophisticated diffusion laws here done by Amailo and Day, which is then very close to the empirical diffusion theta determined by Barkan and Lutz. I want to draw your attention to this dehydration theta here, determined by Clayton and Maeda in 2009. It's nicely corresponds to a theory for breaking of chemical bonds. If you simply take Graham's law and introduce the reduced masses, you will get such low theta values. And Clayton and Maeda very early on dehydrated brucite and also in another experiment serpentinite, generated MgO and H2O. They separated these species directly. It was done in vacuum, I think, and measured the triple oxygen isotopic composition, and they get this very low theta. I think it must be, there's no error reported, but it should be very precise because we have a very large range of delta 18O that is reported here. But kinetic isotope effects are actually not just diffusion or breaking of chemical bonds. And this is one point I want to make in my presentation, is that kinetic effects can be quite complicated. It can be, of course, simply distortion from equilibrium or saying that equilibrium is not reached, but it's also mixing that is often included in these kinetic isotope effects that we observe. So for instance, for the vital effects of corals, I made a small theoretical model where mixing and diffusion and equilibrium all play a role. And I just want to go through this with you. So if you have biogenic calcification of a calcium carbonate mineral down here, up here would be seawater, and the seawater, DIC in the seawater somehow has to be precipitated into this calcium carbonate mineral. So there's a cell wall separating the calcium carbonate and the calcifying fluid, and the CO2 diffuses through the cell wall into the calcifying fluid, and then it has to react to carbonate and bicarbonate to precipitate as calcium carbonate. Now there's enzymes in this lipid bilayer which pump calcium into the calcifying fluid to facilitate this, this precipitation process. And these enzymes pump protons out, so you get a high pH in this calcifying fluid. The CO2 then reacts with H2O, which would be hydration, or with OH minus, which would be hydroxylation to form carbonate and bicarbonate and to form calcium carbonate. Okay, so to make a long story short, we have very different sites in this whole scheme where we might have kinetic isotope effects, and they can be superimposed on each other. So we can distinguish these different processes using triple oxygen isotopes, I think, from this model here. So if you have the delta 18O for calcium carbonate in equilibrium, it should fall on the equilibrium slope. So you have an expectation for the delta 18O, and you also have an expectation for the cap delta 17O. So at 25 degrees in equilibrium, calcium carbonate should fall exactly on this point. If it doesn't fall on this point, it did not form an equilibrium, given that your equilibration line is calculated correctly. So likewise, you have other components in the system that are equilibrated with the water, like the CO2. And if you superimpose diffusion on this, diffusion drives your calcium carbonate to lower delta 18O and to higher cap 17O. If you consider hydroxylation, it's a completely different story. Hydroxylation is the reaction of OH minus, which has a very negative delta 18O value, and I just assumed this theta value here of minus 40 per mil, and it reacts with CO2, which has a very positive delta 18O value of plus 40 per mil. So what you get is a mixing curve. In this reference frame, mixing is on curves, and your mass balance product could plot down here. This is at minus 300 ppm. So the difference between this mass balance point and H2O here, that's the difference between Earth and Mars. It almost reaches processes that we would exclusively direct towards mass-independent processes. Now these species can diffuse faster, so you might have a superimposed kinetic effect, and then you can form carbonate that falls down here and carbonate that falls up here, and you will have re-equilibration. And essentially, the vector that you get for hydroxylation is completely different than the one from diffusion. It may not be like I draw it here, but it's certainly not going to higher cap 17O. It will go to lower cap 17O. And you can now distinguish, if you have a sample with lower delta 18O, if this is due to hydroxylation or if it's due to diffusion. And of course, you can play the game also with water, with the hydration, which then gives you again another vector. And you can have CO2 degassing, which goes again in another direction and is not relevant for the calcification model, but maybe for speleothems or something like this. So what we get is we have a kinetic effect that we observe, which is a combination of various different individual processes. We must understand everything to really predict the cap 17O of our product and to make sense of it. Mixing, this is an example where we have mixing on the molecular scale, but of course we can have mixing on other scales as well. So this is, for instance, from a paper of Sengupta and Pak in 2018, modeling the isotopic composition of ancient seawater from the model of Mühlenbach's extended for 17O, and they predicted that if seawater goes to negative delta 18O, your cap 17O increases, and they made a prediction for the cap 17O composition of sherds precipitated from such a low delta 18O ocean. And as you can see, this is higher than predicted from a modern ocean, and then the Archean sherds are even below that. So to explain the cap 17O composition of these Archean sherds, Sengupta and Pak suggested that this is simply alteration of initial sherd precipitated here on the equilibrium line with pore waters. And so you have kind of a mixing relationship, which has this curved nature and drives the Archean sherds to lower cap 17O and to lower delta 18O values. You can do this with pore waters, or it was also suggested very early on by Naomi Levine that you can have a mixing relationship between iron oxide phases and quartz. And if you mix these, it would also explain the low delta 17O and low delta 18O of Archean sherds, maybe from such banded iron formations. So I plotted in here the metamorphic BIF that we analyzed in the 2014 paper, and it nicely fits to the model. Another example of mixing is water-rock interaction, of course. So if we have materials from the Earth crust, they would fall over here. Materials from meteoric water would fall up here. And if you mix pristine rocks with pristine water, or the 100% alteration end member, your samples will fall on such mixing relations. And you can normally have the pristine rock, you have the altered rock, so you can extrapolate to the meteoric water line and infer the meteoric water isotopic composition. One of the places you can do this is Iceland, of course. The water has low delta 18O, and David Sakharov really has a very nice paper, including not only 17 and 18O, but also deuterium isotopes. And I really recommend reading this paper if you want to get into this. Unfortunately, I do not have the time in this talk, but I want to draw your attention to fossil examples similar to Iceland. Here in the Zulu, we know that we have samples that have quite low oxygen isotopic compositions, down to -11 in this locality here. And the interpretation is that this is due to water-rock interaction of meltwaters from glaciers that are derived from a snowball Earth. So we don't actually know if it's a snowball Earth or if it's a smaller glaciation before or after that. But the idea is that if we now can reconstruct these waters that interacted with the rocks, we can get some climatic information about the Earth back then. Another example, even more spectacular, is known from Karelia in northwestern Russia, here in the Belomorian belt. Ilya Bindeman spent quite some time to study all of these different localities here and reported the minimum delta 18O value, which in this one famous locality, Kitostrov, ranges down to -27 per mil. And Ilya Bindeman even mapped out the delta 18O of these at this locality, and you can see this nice bullseye pattern that was obviously sheared in the tectonic event later on. Both Karelia and the Sulu are reported to be in tropical to subtropical positions at the time of water-rock interaction. So this is really surprising that the delta 18O is so low. One of the problems, if you only look at delta 18O, is that we can infer the oxygen isotopic composition of the water, but we can only tell an upper limit. So we can say the delta 18O was at -30 per mil for Karelia, but it may have been lower as well. And using triple oxygen isotopes, we can infer this better. This is what I did in 2015, starting off with samples from Iceland. These are samples from altered rocks from Iceland. This is the Earth mantle, so corresponding to Icelandic crust. And you can see that the mixing line extrapolated to the meteoric water line gives you a water composition below -20 per mil. And I think it was -23 per mil or so. And it's rather low for Iceland, forcing me at the time to speculate on Ice Age waters being involved in this process, because I didn't have another explanation. It later turned out that the calibration of the in our lab was not accurate. So we had this problem of high precision, low accuracy, and the Earth mantle is actually higher. So the delta 18O of the intercept becomes lower and becomes more normal. However, we did the same for samples from the Sulu and samples from Karelia and inferred these water isotopic compositions. You can see that Karelia is, even if the accounting for the calibration is far away from the meteoric water line, so you still have waters of -40 per mil and lower. And the climate in the Sulu was obviously similar to the climate in Iceland today. So David Zakharov picked this up, and he measured a lot more localities than I did and also recalibrated my data. This is now another representation of Karelian samples. Now the meteoric water line is a curve, meaning that we are now using a CAP 17O that is just calculated from the normal delta notations, which has the beauty that mixing lines become linear, and then it's easier to see what mixing does. So David Zakharov observed these samples here at other localities that indicate much higher delta 18O for the meteoric water. So, and also there's some scatter in Kitostrov, and all this scatter between localities and also within the locality probably means that the meteoric water composition fluctuated strongly from very low to very high, or to normal, let's say, meteoric water compositions. One other explanation could be that the temperature of the water-rock interaction changed. So if you change the temperature of water-rock interaction, you move your hydrothermally altered rock along this way. And of course, you can also change the water-rock ratio to induce some scatter here. But I think it's mainly due to variations in the meteoric water. So this is now a representation of all the data there is, and I recalibrated again, or I did my best to put it on the scale that is now used by most authors in the book. Sorry, 2 minutes? Okay. Yeah. I want to draw your attention to this sample here. These samples contain some biotite, and I wanted to know if the biotite is in equilibrium with the rock and if we can use it. The biotite actually turns out to be not in equilibrium. So biotite samples move over here. They are re-equilibrated, or they are on their way to be re-equilibrated with metamorphic waters that should fall somewhere in this region here. But I also dehydrated one of these biotite samples in the laser or in the sample chamber under vacuum and expelled all the water from it and then analyzed it. And this sample came out down here. So this is consistent with this theta of Clayton and Maeda of 0.505 driving really the 17 down of such dehydrated samples. And I wonder if some of these samples that seem to have too low Cap17O compositions are also affected by some natural dehydration and then just froze in that composition. I'll skip this. Of course, it all goes to the question whether we had a snowball or a slush ball and what the climate was like, but it's still a matter of debate, I guess, or speculation. We can have assimilation of such low delta 18O rocks. So if you have your magma chamber, you produce low delta 18O rocks due to water-rock interaction, you will incorporate some of the low delta 18O rock into your magma chamber. And this is shown here for samples from the Krafler rhyolites, which also have low delta 18O, and they seem to be kind of on a mixing trend towards the hydrothermally altered rocks in triple oxygen isotope space. So that makes sense from these data here. Yes, I will. This is another example of assimilation also by David Sakharov. I will also skip this and also skip this because it was shown by Andreas Pack already, where you have kind of assimilation of mass independently fractionated samples in your rock record. And I will leave you with this summary slide showing all of the variation that we can expect in the crust due to different processes. And you can see it's quite a lot. So I think a lot can be done using triple oxygen isotopes in hydrothermally altered rocks or igneous rocks, etc. So thank you for your attention.
Okay, well, thank you, Daniel, for your talk. And are there any questions?
There is one question in the chat box, if you'd like me to read that.
Yeah.
In case of altered metamorphic rock with unknown pristine rock composition, is it possible to predict the alteration water composition?
Well, I would say it's difficult. You would need something to define the array, and if you don't have the pristine rock, the definition of the array will not be very good. And yeah, even if you have the pristine rock, it's sometimes difficult to predict the water composition. So I think you need the pristine rock to say something.
There is a second question. Do we have time, Andreas?
Yeah, sure. Yeah.
Second question is, do you think that quick hydration of minerals could be traced by triple oxygen isotope values?
The quick hydration. I was speculating about dehydration. I'm not sure, maybe.